paper notes. Okay. So I will make this available to you. It's a little overcomplicated for our needs, but isn't it usually better to have a little more information than not enough? Okay. So, and even the formatting didn't work. Why is there a question mark there? I don't know. Key term right here. You guys put this in your notes yesterday, right? Half-life. If you didn't put it in your notes yesterday, put it in your notes today. The half-life for a radioactive isotope is the amount of time for half of it, for half of a sample of it, to decay into its daughter isotope. Okay? So when we're talking about parent and daughter isotopes, we're talking about decay series. Okay? So in your notes, also make a little table for decay series. On one side, we'll have two columns. We'll have parent isotopes, and in the other column, we'll have daughter isotopes. And again, don't blame me. I didn't decide for it to not be parent and son isotopes or something like that. It is what it is, okay? So we have a few commonly used decay series. What that means is there are a few commonly found isotopes that are radioactive, that's the parents, that will decay into the daughter isotopes, but they're found in things that we want to figure out how old they are. So what would happen is a geologist, I don't know, some kind of scientist is going to get a sample of something they want to figure out how old it is. And depending on which decay series is found in that material, if there is one, they will send it off to a lab. And I'm going to give you the like dumbed down version because I don't have all the details as a high school freshman teacher of how specifically it works. But I've seen a documentary, right? There's this big machine, okay, that takes a pulverized sample of that and it runs it through a particle detector. Don't ask me how it works. I don't know. Look it up. If you want to know, look it up. Okay. But it just counts how many of the parent isotopes are present in the sample and how many of the daughter isotopes are present in the sample. And then you put together a fraction. The one that I like to use is parent over total. So you'd have the number of parent isotopes in the numerator and the number of parent and daughter isotopes in the denominator. Does that make sense? Okay. We get that from that detector counting it up. Now, the different types. Very commonly used for things that were formerly alive. Do you remember from yesterday? What kind of dating do we do for things that were once alive? Carbon dating, good. So the parent isotope would be carbon, specifically carbon-14, and then the daughter isotope would be nitrogen. So if we're talking about that kind of dating, you would either just commonly say it's carbon dating. You could be more specific and say carbon-14 dating. Or you could say, well, we're using the carbon to nitrogen decay series. Many igneous rocks have zircon crystals in them. Zircon crystals contain the parent isotope of uranium. And I believe that's uranium-238, I want to say. Don't quote me on that. I'd have to look it up, double check. Okay, it's probably in this document. And the daughter isotope, uranium, decays and becomes lead. So if we were using this decay series, we would say, well, we're using the uranium to lead decay series. Or I suppose some people in that business might say we're using uranium dating. Guys, the generic term for all of this is radiometric dating. And we use radiometric dating to find absolute dates. we use it to put a number on how old something is. Another one, rubidium to strontium. Somebody do me a favor, look on that periodic table back there, all the way to the left, RB is the symbol. All the way to the left, RB. Am I spelling this right? Is it RHU? Cole, you're right there next to it. Would you mind? Oh, no H. Okay, I just made that up. RUB. Just like that. Okay. I'm just making up spellings now. Rhubarb. I was probably thinking about rhubarb. Oh, rhubarb is so good. Anybody like rhubarb pie? Hold on now. This is a dangerous question. I'm about to be flabbergasted, I think. Raise your hand if you've never had rhubarb pie. I almost had hope because one hand wasn't up. They've never had rhubarb pie. That's sad. Okay. If you get a chance, and I know there's the strawberry rhubarb too. I get it, and it's good. But I'm a purist, okay? Rhubarb pie, excellent. So rubidium to strontium, that's another DK series. And then there's another one. Oh, argon, potassium to argon. Okay. Those are probably the most common decay series that are used to date stuff. Okay? They each have their own limits. As an example off the top of my head, carbon-14 dating can only be used back to, I think it was like 40 or 50,000 years. Any older than that, and there's just not going to be enough parent isotope left to get a good, accurate assessment on the age of that sample. Some of these, I want to say it was a potassium to argon. I want to say it's like really, really long, like really long half-life. I forget which one it is. The half-life is actually older than the assessed or the current estimate of the age of the universe. So in other words, that stuff's going to be around for a long. So it's radioactive, but it's kind of stable. It takes a very, very long time for it to break down, if that makes sense. Okay. One last thing, because you guys are one of my probably top 2 classes as far as speed and picking stuff up. Okay, so I'll give you a little extra. If you find these on the periodic table, do you guys still have your periodic tables in your notes? Either pull them out or just look at the one on the back wall. Find them. So carbon and nitrogen, where are they in relation to each other on the periodic table? Right next to each other. In fact, carbon is one element preceding, one before nitrogen. So you might be thinking, well, wait a minute, how can decay cause it to become bigger? Might you have that thought? So hold that one there. Find another one. Find uranium and lead. Uranium is all the way down that bottom row that they pull out, 92 atomic number. You see it? And then find lead. I believe that's what, PB, right? Where's that at? What is it? Is that 82? Much lower down on the list, right? 10 protons fewer to get to lead. Do you guys see that? Okay. Now that one makes perfect sense. That's decay right there. It's really dropping in size. Okay. So the difference is what type of decay. Carbon and nitrogen, potassium, no, not potassium and argon. This one, I don't know them all off the top of my head Carbon and nitrogen is beta decay. And when that happens, you have one of the neutrons breaks down. It ends up shedding an electron. It kicks the electron out of the isotope completely. And then what's left behind is a proton. So it gains a proton and kicks out an electron. One of the neutrons ceases to exist. Basically, in beta decay, a neutron becomes an electron that gets kicked out and a proton that stays. So it graduates. The technical term is transmutates into nitrogen. Does that make sense? Gregory type? Does that make sense? Okay. Whereas uranium to lead, that's an example of alpha decay. And in alpha decay, you're actually losing alpha particles. And each alpha particle contains 2 each of protons and neutrons. What are you talking about? No, I want to know, what are you talking about? What is the conversation about? You're a liar. And I don't mind saying it because by golly, I'm an honest person. So if you're talking and I say you're talking, don't say I'm not talking. That makes you a dishonest person, yes? Okay. Guys, the alpha and beta decay, I'm not going to hold that to you. I'm not going to hold that to you. You're not going to be counted. You'll get that again in chemistry. Okay? Probably, I hope. I waited too long. It's cold again. Got to avoid Blackburn's trap over here. He's trying to trip me. He's probably got a club ready to knock me out. Okay. Questions on that? Decay series are parent to daughter decay series. It starts here. The parent isotopes are what? Starts with an R. They're unstable. The word for it starts with an R. Huh? Radioactive. Isn't there a song? Imagine Dragons. Isn't it Imagine Dragons? There's a song. Radioactive, radioactive, right? And then the daughter isotopes are the more stable thing that it transmutates into, decays into. All right, I'm boring the heck out of you guys. I'm sorry. We're about to do some math. That'll liven things up a little bit. Ham, what you doing over there? Can I erase this? Nobody really needs to be on their computer. You're in your paper notes today. That's why I said paper notes. I didn't say paper notes and computer. I just said paper notes. Oh, you probably missed all that. Elijah did too, because he doesn't have any paper notes out. You're going to draw. Okay. I don't know how you're going to draw some of this. All right. Now, making the table, you should be able to do just fine. You guys remember the table from yesterday? Try not to look at your notes. Let's see if we can redraw the table. Do you remember the half-life of carbon-14? $5,730 years. Good. And that's how much time would have gone by after one half-life. After one half-life, how much of the parent isotope, the carbon-14, is left? Just one half. After two half-lives, how much of the parent isotope is left? A quarter. After three half-lives, how much of the parent isotope is left? 1/8. And then what would the number be here for date, or how old it is? And after 3? Very good. All right. So you're going to run it through a pulverizer, your sample. Then you're going to run it through a detector. It's going to spit out numbers at you, and you're going to form a fraction with those numbers. The fraction will be the number of parent isotopes over the number of total isotopes in that decay series, from the decay series. Are you okay? So let's make up a fraction, huh? Somebody give me a number between 2 and 5. 3. I heard 3. Somebody give me a number between 11 and 13. I said between 11 and 13. 12. There's only one number in between 11 and 13. Gotcha. How old's our sample? Quickly, quickly. Huh? 1/4 is not an age. How old is our sample? 11,460. 3/12 is the same as 1/4. It's right on our chart. That was easy. Okay. I was just waking you up. How about we do, we'll stick with 3. 3/30. How about 3/30? I'm going to see if you know what to do. We've got to figure out where it goes on the chart, right? Where our sample fraction goes on our chart. I'm not doing it for you. Where's it go? I can ask questions. Is 3/30 bigger or smaller than a whole? Smaller. Is it bigger or smaller than a half? Bigger or smaller than a quarter? Bigger or smaller than an eighth? Smaller. Do we need to add on to our chart? One what? 1/16. And how old would our sample be at 1/16? It'd be another 5,730 years, right? What would that be added onto there? 22. Help me out. You guys got calculators? Huh? If you don't have a calculator out right now, get a calculator out right now. Otherwise, you guys need to be doing it on paper. I'm fine with that. I'd be ecstatic if I saw you guys doing it on paper. No.
We are ready for one roster of the second session, the agribusiness. Only look at the agribusiness list. Students that are listed on that and are taking the test are going to go to the help room across from the choir room. They can head there now with their backpack. Thank you.
Go. 22,920. Is that what we got, everybody? Good. Okay. Is 3/30 smaller than 1/16? I have a yes. I have a no. If you're not sure, how could you easily find out? You can simplify it. What do you mean by that? Because I don't know any way to simplify 3/30. Do you? With your calculator, what would you do with your calculator? One-tenth. Okay. So 1/10. Where does 1/10 go? Is 1/10 smaller than a 16th is what I'm getting at. Good. Oh, it is. It isn't. I'm confused. Is 1/10, if I take a whole thing and I cut it into 10 pieces and I take one piece of those 10, is that one piece of 10 bigger or smaller than one piece of 16? It's bigger, right? So 1/10 goes in here, right? Everybody follow? Good. Same thing. Good. Remember what to do next? Anybody remember what to do next? Why? You're missing a step. What we're going to do is we're going to take the row above and below our fraction, 1/10. We're going to turn them on their side and open them up into a number line. A number line and at the same time a timeline. So check this out. On this side, we're going to have 1/8. All the way on this side, we're going to have 1/16. And then our number, 1/10, falls in here somewhere, yes? If you're using pencil, don't write too hard because you might be doing some erasing. Or maybe just a line strike through. That works too. Now, at 1/8, how old would our sample be? And at 1/16, how old would our sample be? 22,920, right? So now we have a number line / timeline. We need to figure out where exactly our fraction goes on it. But to do that, we need a least LCD, a least common denominator. Good. Between 16, 10, and 8. What could we use as a number 16, 10, and 8 that all three of those will go into evenly? Hmm? 2? 8 can go into 2? 10 can go into 2? Only two numbers that I'm aware of can go into 2 evenly. It's 1 and 2. This is not a pause, a dramatic pause. This is me waiting for you to tell me what's the least common denominator between 8, 10, and 16. 80? Does 16? Obviously, 10 and 8 go into 80. Agreed? Does 16? Perfect. Okay. So if we're making it 80, what is 1/16 of 80? In other words, what's 80 divided by 16? What is it? 5? So we have 5/80ths. And now, if you don't want to erase, you can just put a line through. That way you can kind of still see it there, I guess. And then if we're making 1/8 80, well, what's 80 divided by 8? 10? And what's 1/10 of 80? 8. Okay. 5, 8, 10. In order, common denominator. What's the difference between 5 and 10? What's the difference between 10 and 5 or 5 and 10? Nope. The difference is the same. The absolute value of the distance is the same. Is that better? Technical. He's very technical. That's good. What is it? What's the absolute value of the difference between 5 and 10 or 10 and 5? You're going to get technical, but you can't give me the number. What is the difference between 5 and 10 or 10 and 5? 2? What math do we do if we're looking for a difference? Mister, I know what absolute value is, but you don't know what subtraction is? So 5 minus 10 is what? negative 5. 10 minus 5 is 5. I thought he got me on the absolute value thing. They both have the same absolute value. It's 5. Now I'm not so sure because he didn't know what a difference is. So if you're finding the difference between numbers, you're finding how far removed are they from each other, right? So 5 and 10, no matter which way you're going, it's 5. All right, so in other words, we're cutting this into 5 pieces, right? Check it out. 6, 7, 8, 9, 10. See what we're doing there? Can you do that on your machine there, or do you want to do it on paper? It's up to you. You don't need to know how to do it. I'm showing exactly how to do it. I'm modeling the behavior. Do you need paper? Okay. So we have just physically divided our number line into 5 pieces. That means for each of these increments, there is a corresponding amount of this is both a number line and a timeline. So each of these increments is the same amount of time. How much time is each of those increments? What is the total amount of time on our timeline? And it doesn't matter where our sample falls, because you're always going to be in between from one number of half-lives to the next. And every time you go to the next one, you're just adding another 5,730 years, yes? So it doesn't matter if we were between a whole and a half and a quarter and an eighth and 16th. Doesn't matter where we are. Your timeline is always going to represent, if you're using carbon-14, your timeline is always going to represent one half-life, which for carbon-14 is 5,730 years. Does that make sense? So if that's how much time we have here, and I just physically divided it into 5 pieces, what would you do with a calculator? I don't understand. I don't get it. What are you laughing at? Where's your paper notes? In their lap? Are they in your lap? No, him. You just don't want to? We just don't want to. Okay. Well, I won't have any pity for you when you don't know what the heck you're doing. Okay, so do it. What are you doing? Flusher, what are you doing right now? Aren't we taking the total amount of time on our timeline and dividing it by 5? Because that's what we physically did, right? So what is 5,730 divided by 5? 1,146? Is that what everybody got? So each of these increments is 1,146 years of time. Our sample was 1/10, which is right here. This is our sample. It is how much older than this end of the timeline? 1, 2 increments. each increment is 1146 years. So you could do it a couple different ways. You could take 1146 times 2, because that would be this whole amount of time right here, and add it to 17,190, and you'll get the age of the sample. Or you could say, hey, 1146 years for each of those increments, 1, 2, 3. So 3 times 1146, and then you could subtract it from 22,920. See how you could get it from either end of the timeline. Does that make sense? Don't worry, if you don't get it yet, this is our first one of the day, right? First one of the day. We'll do another one or two. So what's our age? I'm not suggesting that you do it. I'm telling you to do it. What is it? You're not going to have a negative. What? 19,482. And you got that by taking 17,190 plus 1146 plus 1146. Or did you do something different? Did you multiply it by 2 and then add it to 17? Okay. So he took 1146 times 2 and added it to 17,190. More than one way to skin a cat, for those of you that like skinning cats. I am definitely going to skin my cat, Murphy. When he dies, I'm going to skin that cat, and he's going to make the most luxurious neck warmer. I decided, guys, he was like 1 year old, and I'm like, that is the most luxurious fur I have ever felt. It is like, ooh, it's nice. Just saying. Don't give me a dirty look. If you felt how nice his fur was, you're like, yeah, that's a neck warmer right there, for sure. Well, what else are you going to do? Just bury him? What a waste. What an absolute waste of a beautifully just comfortable neck warmer. It's less creepy than, well, maybe not less creepy. Some people like to actually stuff their dead animals and like put them up on the, like, you know what I'm saying? They put them up like on a shelf or something, like, oh, hey, Murph, how's it going? He's dead. You might as well wear him. Are you awake now? Okay.